Hello everyone, today we are covering lesson 1.4 on continuity and one-sided limits. So we will open up by discussing what makes a function continuous. And in a graphical sense, a function is continuous if it is uninterrupted. So I can give you the example here. A function like this would be continuous because it is not interrupted at any point on the function. But if a function can be continuous, it can also be discontinuous. And there are actually three types of discontinuities. So the first type is a removable discon dis discontinuity, and it is represented by having a hole in the graph. Um, Something like this would be a removable discontinuity. You can see there's a hole in the graph here, and the graph is not continuous. So the second type of discontinuity is an infinite discontinuity, and it is represented by having a vertical asymptote somewhere in the graph or in the interval that you are trying to decide is continuous or not. So a function like this would not be continuous at x equals, say, 4 because there exists a vertical asymptote here. The third type of discontinuity is the jump discontinuity. And this means that even though um, say FC exists, something like this, see here, FC would exist, but the graph is still not continuous because there's a point here. So all these have a mathematical definition as well. So here, it just means that the function is undefined if x equals c. The jump discontinuity is that the limit of fx does not exist at x equals c, and we'll talk about later what defines if a limit exists or not. And then at the jump discontinuity, it's that even though fc exists, the limit of fx at that point does not equal fc. Now moving on, we can discuss one-sided limits because it's so closely tied to continuities. So I can give an example here of a one-sided limit. One-sided limit. So provided that C and L are real, are constants, limit x approaches C plus equals L, and limit x approaches C minus equals L. Now, the plus or minus sign here represents which direction you are approaching point C. The plus means you are approaching from the right side, and the minus means you're approaching from the left. side. So here we can see it on a graph. Uh, this would mean that you're approaching from the left, so we would get a L value of here, but this means we're approaching from the right, so down here we will get a L value of this. And this just directly ties to whether a limit exists or not. A limit has to, if a limit exists, lim x approaches c plus equals L has to equal lim x approaches c minus equals L. So we can see here that this limit would not exist. Moving on, we can talk about how to determine if a function is continuous or not. So if c function is continuous on a closed interval, there's actually a theorem for this. So if a function is continuous on the closed interval a and b, lim fx x approaches a plus and sorry equals fa and lim x approaches b minus fx equals fb, then the function is continuous from the right at a and continuous from the left at b. And this is important for a wide variety of theorems, and I'll give an example here. So say we want to find out if this function is continuous or not at the closed interval of 1 and -1. We can evaluate the limit, which is -1 minus x squared equals 0, right? And then here we can see that limit x approaches 1 minus x squared equals 0. And we can conclude that the function f is continuous on the closed interval. It's continuous on the closed interval -1 and 1. Now, moving on to some of the properties of continuity and some of the common functions that are continuous. Now, there are a couple, and I will list them here with appropriate examples. So, let's see. So, the first type are polynomials. And now these functions are continuous on every number in their domain. There's one exception that I will get to and point out later. So an example of a polynomial would be something like this, right? And then moving on, we can discuss rational functions, which would be something like this. However, this is like the same rule applies except at the points plus or minus 1, because then this would be 0 and it would be undefined. Now, root functions also obey this rule, and if we can see here with this simple example of a root function, trig functions too. And here, and then an inverse trig function as well. and exponential functions. And finally, log functions. Now, all these functions are continuous at every number in their domains. And then moving on, we can talk about some of the properties of continuity. So provided that both functions fx and gx are continuous at x equals a, and c is a constant, the following four functions are continuous. So the first function, fx plus or minus gx, is continuous. The second function, fx times gx, is continuous. The third function, the constant times fx, is continuous. And the fourth function, fx divided by gx, is also continuous, provided that, of course, gx does not equal to 0. Now, moving on to perhaps one of the most important theorems in calculus, the intermediate value theorem. And it states this. So if f function is continuous on the interval a and b, and if n is a number, this is very important, strictly, right, between fa and fb, then there exists a number c in this fa and fb such that fc is, and this can be used in a variety of problems. So I will give an example here. So if you wanted to show that the that there is a root of the equation ex minus x squared minus 1 over 2 equals 0. Now, first we have to say that this function is fx. Well, fx equals to this. Now, first we need to find numbers a and b such that fa is larger than 0 and fb is smaller than 0. So here, let's say f0 would be e to the 0 power minus 0 squared minus 1 over 2, which is 1 over 2, and it is larger than 0. And then we can also get f1 equals e to the power minus 1 squared minus 1 over 2, and it is e minus 3 over 2. And we can kind of approximate that this is also larger than 0, which means that, unfortunately, some of the more simple solutions can't be used. So here we can try f is -1, and so e is power minus 1 squared minus 1 over 2. We would get 1 over e minus 3 over 2, and we can kind of approximate that this would be smaller than 0. So, since the function f is continuous on the interval on the interval -1 and 0, and that f smaller than 0 and f 0 is larger than 0. So by the intermediate value theorem, there is a number c in between of -1 and 0 such that fc equal to 0, and we have just solved the problem. So that's all for this section. I hope you understood it, and I'll see you again.